Okay, now I'm all set up. So I usually walk around a lot when I talk, then I should not be doing that. So, what I now work on, the kind of problems I work on nowadays are still algorithms problems, but they're mostly geared towards questions that come either from trying to scale whatever you're doing on very large data sets, or the algorithms problems that or the optimization problems that come out of trying to solve all these very very interesting machine learning models, trying to fit these machine learning models, right? So I wouldn't call myself a machine learning person, but of course, if you're trying to design a particular algorithm to what I call scale a machine learning model, there are certain trade-offs you have to do, right? I mean, there's nothing that comes for free in life, and we'll see some of the trade-offs in the particular story that I'm going to talk to you about. And I mean, this will also give you a kind of clue as to what are the kind of tools you need to build for yourself. You need to skill yourself in order to look into deeper into the field. So it's going to be a very light talk, very much about getting into all the technical details, but most of the technical details will give you only a flavor of it. So here's the story. So we know all about big data now, right? And this is one particular picture I kind of found from I don't know, something like data8.org, domo.com or something, huh? And they're kind of trying to impress upon you what is the rate at which, not just the quantity of data that we have, what is the rate at which the data is growing, right? Every second, for instance, this is every minute per day, whatever is happening, right? Apple is getting 47,000 app downloads per day, and you're getting so many YouTube users upload 48 hours of new video every minute of the day. So if I just look at myself, for instance, I mean, the kind of YouTube videos I have lined up will probably take the rest of my life even to watch these, right? So there's no way we are able to digest all this data meaningfully. Even the fancy algorithms with all their with the fancy machine learning algorithms, with all the supercomputer power and the distributed computing power that Google is sort of handing towards sort of fitting them with, even then we'll see that it becomes very hard to actually digest all these data in order to make some sense out of it. We'll see a very very small example, a very very simple question. We'll see how that turns interesting. So imagine this. Okay, so imagine this. So you have done. Okay, no moving. So you have done a nice bachelor in computer science degree. You took a fancy job, and then you go to your fancy job, and then you. I mean, it's a cool company, right? So you're even wearing shorts on the first day, and you have colored your hair. And then I mean, this company has a bunch of different portals, right? It has some finance, maybe a couple of music portals, a sports portal, and a lot of different other things. And the first thing your manager tells you, the dude, I mean, this is all very interesting, the kind of things that you have done. Here is what I want. I want you to build me a company-wide real-time analytics system. First of all, you really have no clue what that really means. So you're asking for yourself, what should I build a LSTM model? Should it be a CNN? Which deep learning architecture, or should I just bring in blockchain? What is it exactly that you mean, right? And of course, I mean, being the clever chap that you are, you realize there's no point asking these questions without understanding what is really being asked of you, right? So you go back and look into the data. You say that, okay, what does it really mean? You understand at a very high level what analytics of the analytics system might mean. At a very intuitive level, it says that, okay, look at the data that the company is getting, the user data that the company is getting every minute, every second, and try and help me make sense out of it, right? Help me make sense out of it so that I can answer broad, high-level business questions that say that, okay, we are retaining customers or not, customers come back to us, to our portal or not, I mean, or they're leaving at a particular rate, we're losing customers at a particular rate. I mean, the time that the customer spend in our portal on an average is this many seconds per day, and these are incredibly important business questions, right? And what is the kind of underlying data that you have? Well, really, I mean, there's a variety of different kinds of data, but here, I mean, these are possibly the largest sources of data. If you look at the kinds of data, I mean, email is I mean, if the company that we're talking about is Google, Email would have been one kind of data. But really, the largest volume are these things called the weblog data, right? Which essentially keep a record of everything that you do while you're on the company's website, and even sometimes when you're off the company's website, if that company happens to be Facebook. And these are two examples, right? So there's a table. There are two tables that you see. In each table, you maybe have a user ID, right? And this might be a unique user ID if you have logged in. If everybody has to log in to sort of use this particular service, or it may be what we know as what we call a browser cookie, right? And then there is some record of what this person was doing. So here this says that this person was visiting apps. She spent 59 seconds in this particular session and viewed 5 different items. And that particular, the U1 user ID, again visited apps and purchased something called Facetune and paid so much money. So let's just look at these two types of data. And then what you are pondering for yourself is that how can I help make sense out of this data? So again, one other principle is that, at least for me, is that start simple. What is the simplest question you would ask, right? And you start with the most basic question, and then you're trying to say that, look, you go back to manager and say, look, do you even have a sense or a way of measuring how many distinct people are visiting your website per day or per minute, right? Or how many of them what fraction of the distinct people who's visiting tomorrow are coming back, who's visiting today are coming back tomorrow, right? Because clearly, being again the sort of smart internet user that you are, you know that there's a difference between these two types of weblogs. Let's say in one of them, you have 25 million visits from only 2 users. In the other one, you have 100K visits from each of 50 users over a span of 1 month, right? Or let's say you have 10 visits from like 10 million users, right? So there's a difference between the two, because possibly in the first case, it's really a bot that's hitting on your website. In the last case, it's probably a set of loyal users who's coming back over and over and over, right? Even getting a handle on this number of unique users who's coming, and further being able to answer these kinds of estimating repeat users, how many unique users are members are visiting 2 different portals, doing multiple things together. These seem to be important questions, right? So how would you do this? So here's my first, ball thrown at you. So I just give you any of these tables, right? So suggest me a method of finding the number of distinct user IDs. And in the first, there's a particular column, distinct user IDs. So, but for every user, there are multiple rows in this particular data set of course, because a same user might be doing multiple things. So what would you do? A very simple question. What would you do? Any idea? Beautiful. So take the column and take set out of it. Now the question that you have to ask is that how much space is that going to take? How much space is that going to take? Order number of distinct users. Beautiful. What is and if you didn't want to take that much space, right? What are some other things you could do, right? So here is one other thing I would do, for instance. Okay, if I could sort the column, right, in terms of the user IDs, right, and once I sort the column, then all the user IDs that are same will be in a contiguous interval, right? And then I could just go take one pass along the sorted column and just do the count. Well, then you'll complain, then how are you doing the sorting? This is if you're not using that much memory. And we have hit upon the basic issue, right? That how will you solve this problem if you're not able to load the entire data set into memory, right? And let me give you some estimate of the kind of numbers you might be dealing with, because remember, this is your dream job. This is not some small company that you have gone to. One such table, let's say for instance, it has 10 billion rows, and I'm not making up numbers here. And each ID could be 256-bit. Each user ID could be 256-bit, which is about the size that each of your Facebook ID is. So, yeah, I mean, using those numbers, if you just do a back of the envelope calculation, you will see that even the, building a set takes about 3 terabytes of memory, right? And the problem is that you might say, okay, I have 10,000 machines, but if you have distributed the data over these 10,000 machines, distributed the table over these 10,000 machines, in order to build a set, you still need to pull it together, right? So it's the communication that you're paying for. So either way, you have at some point you're either paying for communicating this data over this network back and forth, this huge amount of data over this network back and forth, or you're paying for storing this data, this 3 terabytes of data in memory. And anyway, being the first day in your job, you don't, you've been given a teeny machine memory, and you don't want to go on asking for a lot more. You want to show how smart you are, right? And furthermore, this will not really scale once the company grows bigger, and or even if you're looking for larger tables, right? So here are again some variations of the over the kind of things that you say. We could also keep a bit array instead of a set. Essentially the same idea, except that the size of the bit array has to be the size of the universe, right? And what you do is that once you keep the bit array in memory, you scan that entire table, and then you turn on a bit. If you see that particular user, every user corresponds to exactly one position in this bit array, and this would be exact, right? The point is that what you know is that if you know a little bit of information theory, right, you can try to argue a manager that look, I'm giving you seemingly dumb solutions, right? Because these are naive solutions, and they're not dumb solutions, they're naive solutions, but they can't really do much better if you're looking for exact solutions, right? And I can prove this because I have done a class in my BTech called information theory, which essentially says that if you have this much information, how many bits do you need to store that much information, right? If the uncertainty in your data is so much, how many bits do you need to store that data? And that's without going deep into it, that essentially says that how much space you need to solve this particular problem exactly. Well, the manager says nothing doing. You have to solve the problem on the machine that you have. Then you go back and argue, why do you need exact values, right? And what would you, if you're really sort of are a company having like 100 million users, do you really care if it's 100 million and 1, or 100 million and 2, or 100 million and 1,000, or just that number around 100 million is fine, right? And you really want to distinguish whether it's gone from 100 million to 90 million or 100 million to 110 million. That's really the order of magnitude that you're really worried about. And then you settle for what is known as randomized approximation algorithms. What does that mean, right? Without going too much into the terms, what it says is that number one, you have to convince a manager to give up these two things. You're not going to return an exact answer, right? Your algorithm might sometimes fail. However, now your manager has two things to write in his or her annual performance review. That okay, I have two parameters in my hand, right? One of them, the smart guy has told me that this is called epsilon. The smart guy or girl has told me that this is called epsilon, which is going to control the amount of error her algorithm is going to do. The amount of error her algorithm is going to do in the worst case. And the other is the confidence, right? Which is going to say how much confidence, basically captures how much confidence we have in that estimate. Right? So this is not exactly statistical confidence, but it's going to say that with probability, if you put this delta to be 1%, it's going to say that with probability 1 minus 1%, that is 99%, I believe that the estimate lies within, let's say, 0.1% of the true value. This is a kind of statement your manager can make, right? And those two quantities, the amount of error that your algorithm is going to make, and the amount of confidence we're going to have in that, she can supply to you, and you can sort of fit in that into your algorithm. It's going to need a correspondingly scaled. It's going to scale the resources correspondingly. But remember, these are still constants, small constants, right? And then you still have an algorithm. The question is that even this is not clear, that this is possible. It's possible to do it this way. Okay. So these are what we call epsilon delta approximation algorithms. I promised to have small number of equations if I haven't deleted. So hopefully I have deleted the sides of the most equations. But basically, what he promised is that this is what's going to happen. That suppose the true answer is n, which is the true number of distinct users in a particular data set. What you're going to return is an estimate n hat, and you promise that n hat is going to lie between 1 minus epsilon n and 1 plus epsilon n. So think of epsilon as 1%, for instance, and that this guarantee is supposed to happen with probability 1 minus delta, or whatever epsilon and delta your manager gives you, right? And the probability here is over the randomness of your algorithm, right? It's not about the data. You're not assuming anything about the data. Your company can show you the however bad data that you that they want, and it's going to work for that, right? So what is the next step? So now that you have convinced the manager to give you some leeway, well, you have to meet certain people, right? So you take either this time machine, right, and meet this guy called Philip Flajolet, a genius French mathematician, who lived until pretty recently, and who's done a bunch of very interesting work on something called analytic combinatorics. Although we're really not going to visit that, except if you ask me specific questions. And who's done, in addition, something to very much of your interest called a probabilistic counting algorithms. Okay, I'm also told he was a very colorful character. So then let's see what does he have to say about it, right? So what he tells you is that, look, dude, you have to build something called a sketch, right? Now, it's not the kind of sketch of a, when I say the word sketch, it's kind of overused. It's not the sketch in terms of that you're building a sketch of a character. It's more in this mini-me sense, right? That you are interested in Dr. Evil, but Dr. Evil is too big. You can't handle his entire corpus. It's too huge, right? So you build a mini-me version of it. So I think this reference may be too old for the people out here. I'm sorry if you are missing this reference. And basically, the idea is that if you have your entire data set, right, and you don't have the resources to work with your entire data set, what you do is that you build a compact version of it somehow, right? But you have to build a compact version in a smart way, right? You have to build a compact version so that by looking at the compact version, you're able to answer questions almost as accurately as you would have by looking at the huge version of the real version of the data set. And you have to be able to guarantee this, right? And he does guarantee this, right, for the particular question that you're interested in. So let's just see how, right? So not just at this, because once you build this particular tool, right, this can be used in a bunch of other settings, right? If this company does a lot of machine learning, here is a particular application, right? If they're building, language models, there's something called a k-grams, which is essentially, if you take key tuples of words in any text. This is called a k-gram, right? And these are very useful for language models. And sometimes what you want to ask is that what is the distinct number of k-grams that you see in a typical English corpus, a huge English corpus, right? You might also, if they also have something like Google Hangouts or Skypes, they might also want to ask, okay, I have all these log data that are generated by the calls. I want to see how many distinct people are using my call service, right? Again, it comes back to the same question. It turns out that if you are able to answer this question efficiently, if you're able to build a software that basically any engineer in the company can just deploy without having access to the company's what we call the huge distributed platform, it might be a game changer for the company, right? And it's going to help specifically what we call the real-time analytics for the company. So here is my first part, right, in building what we call a sketch. Right? And I'll just tell you what the approach is, and you're going to tell me if it's good or not. Right? So the proposed approach is as follows. So imagine that the length of so when I call a stream, imagine it's a file stream basically. You're reading the data set from beginning to the end. So imagine that I say that that length is m, right? But of course that there are repeats, right? So the universe is the universe of user IDs, and the size of the universe is n. So n could be depending. So assume your data, assume your file is very huge, right? So assume that the universe size maybe is less than n. It doesn't matter so much. And here is what I propose, right? I sort of, instead of looking through this entire file, I sample certain rows of the file. I sample certain rows of the file, and then I only sort of look at those rows and throw away the other rows. Okay, so so just to make it concrete, if I were to have this particular file, maybe I say that, okay, I sample row 1, row 2, and then I mean maybe row 1 and row 4. And then I mean, just by randomness, I happen to sample row 1 and row 4, and then I look at the number of distinct users in that sample that I have, right? And then you have to scale it up, of course, and you scale it by saying that, okay, if I have sampled S rows, right, out of the entire set of rows, and if n hat is my estimate, then I have to scale it up. And scale it up by the factor m by s. So s is less than m, of course. Because you want to solve the problem on a smaller data set. So is this a good algorithm? What do you think? If it's not a good algorithm, what are the kind of data sets on which this is not a good algorithm? So here's one particular data set, right? So imagine that there is one very sort of promiscuous user who keeps on coming back to your keeps on coming back to your portal over and over and over. Basically generates a lot of activity, right? So that particular user has contributed a lot of rows to your data set, which is user 1 here. Every other user has contributed a small number of rows. In this particular small example, only 1 row, right? So what will happen? What will your algorithm do here? What kind of mistake? Will it work well here? Will it not work well? Because you're sampling rows. And then you're estimating the number of distinct users in that small sample. What will happen here? So to assume that the number of rows m is much larger than the number of distinct users here. So if you take like 10 samples, 10 is just a number. What do you expect to see here? Only the ones basically, right? That unless you take a huge number of samples, you really will see only the ones. And so the number of distinct users you will return is 1, right? Whereas the number of distinct users is actually very large, right? And potentially, and it's very large. But it turns out that your data set is much larger than that. Your number of rows is much larger than that. So you don't get to see them, right? So so this algorithm is kind of hopeless. Okay. So so here is one other algorithm. I mean, again, sort of again modified by by this bit array. We're going to modify this this set or the bit array idea that we have, and we're going to turn it into a somewhat reasonable algorithm, right? And wait, I'm running with you. So who's coordinating time? Really? You should not say that. That's a pretty dangerous thing to say. So around 10 more minutes. Okay, let's say 10 more minutes. Okay. So so here is what we'll do. We'll still keep a bit array, right? But we will not. But we will tune. I mean, we get to tune the size of the bit array, right? Because I mean, we can't keep a huge bit array, right? So we'll keep a bit array of some size m. This m will be controlled by the size of the memory of the machine that you have. Basically, it's in your hands to set this m. And what we'll do is that we'll have what we call a hash function. I mean, essentially, it's a function that maps every element of the universe to one of these positions of the bit array. And when you're seeing a particular item, you go and set that bit, right? So what is the, why will this not be exact? I mean, what will you do after you set the bit? Of course, the natural thing to do is to count the number of 1, is to count the number of bits that have been set to 1. So why will this not be an exact algorithm? Why will this make an error? Sorry, because we're controlling the size m. Yeah. So potentially the size m is much smaller than the possible number of user IDs that you have. So there'll be collisions. That's what you're, I think that's what you're trying to say. So there'll be collisions because you're mapping up a large thing, a large thing. You're trying to pack a large number of things into a small number of things. Of course, there has to be collision, right? If you remember something called a pigeonhole principle. But then you have to be able to deal with these collisions, right? How do you do that? Turns out, I mean, you can still come out with an estimator that's not so bad, right? And I'm claiming that here is the kind of estimator, right? You look at the number of entries that remain 0 in the table, right? And then I'm claiming that your estimate for the number of distinct elements is this. It's m log Zm by m. So remember, so note this interesting thing. If the same user ID comes appears in 2 different positions in that in your data set, they still only turn on only 1 bit because the hash function maps both these incidences to the same thing, because the function is really a function of the user ID. It's not a function of the row, right? So I mean, so the same element appearing 10,000 times doesn't matter. That's not a matter of concern here, at least. So you return. I'm claiming that you can kind of return an estimate that says it's m log Zm by m. Oh, so why is that? I mean, and this will give you the kind of this will give you an intuition of the kind of probability that you need, which is not very hard, right? So so first you kind of calculate, okay, what is the probability that a particular bit, let's say bit number 1, remains 0? Well, you take one of the user IDs, right? And then you say that, okay, what is the probability that this user ID was not hashed to this particular position? Let's assume that you are dealing with a random hash function that sort of sprays the user IDs over these m positions uniformly at random. So then the probability that the first user ID does not sort of map to this particular position 1 is really the probability that it maps into one of the other m minus 1 positions. So it's m minus 1 by m, which is 1 minus 1 by m, right? And the same has to be true for all the n user IDs that you have seen, right? So then the probability that the first bit remains 0 is basically the product of all these things, which is 1 minus 1 by m to the power n. And this you can approximate by some exponential power. And based on this, you can say that, okay, what is the expected fraction or expected number of positions that I still expect to remain 0, right? And that you can get just by a simple, what we call the linearity of expectation or something, and you get that formula. It's a very simple formula. You just sum up those probabilities, right? Because each of them behaves like a coin toss. I mean, it's what we call a Bernoulli random variable, right? And then you get the expectation of the sum of Bernoulli random variables, and then you can apply fancy things to say that it's not just expectation. The random variable really stays around this point, and so on. Turns out that even this is really useful when the size of a bit array is almost the kind of probability guarantees that you see is really useful when the size of a bit array is almost the size of your universe. So not that useful. And here is where Flajolet comes. And he says, forget this. He's a Frenchman. And then he says that, okay, I'll solve you this problem, but the amount of space that I take will only be logarithmic in the size of the universe that you have. So if you have a universe of like 2 to the power 256 elements, I'll solve you in 256 bits. Well, times 5 or something, or times 10. And he promises to do this. And he says that, but you have to bear with me and understand what we're trying to do. What he will say is that I'll again have something called a function. He names it a hash function. Well, he doesn't name it a hash function. It was named before that. And then he says that this function gives you a L bit string for some L that I'll tell you what it is later. For some L, it gives you a L bit string for every element of the universe, right? And think of this as a uniformly, think of this as for every element of the universe, it's like you're doing MD5 and you're generating almost a random L bit string, okay? And you have to have a very simple function, right? And this is what you have to code down. You have to have a function that counts for every L bit string V. So V is a L bit string. It says what is the position of the rightmost one in the bit representation in V. V already is a L bit string, so I should not have written a bit representation, right? And for instance, just to see an example, if this is V, then the zeros of V gives you this particular value. Let's name this position 0. This is position 1, this is position 2. The zeros of V is this, is 1. Zeros of V for this particular V is what? 3. because this is 0, 1, 2, 3, right? And once you code up this, you understand this definition, you also see that there's a mathematical sort of meaning of it. It says that this is the maximum I such that 2 to the power I divides B, because this gets divided, I mean, this is divisible by 2 to the power 3 and not by 2 to the power 4. This is divisible by 2 and not by 2 squared. Okay. So and then actually this algorithm was suggested to him by somebody called Nigel Martin, and I mean in a slightly different form. Then it sort of intrigued him so much that he kept on thinking about it and saying that why does this work? But I'll just tell you what the algorithm is first. So here is the algorithm. It says that look, it has to be a very simple data structure, right? It really has to store one particular quantity. That's it. That's all, right? So you start off with a call to this data structure for this thing called initialize. Well, initialize first creates a hash function, and then it also initializes a small counter to 0. That's it. And then you process the data set, whatever data set that you have, one row at a time, right? And you're only looking at the user ID column because that's the only thing of interest. And then, first of all, you calculate h of x. Remember, h of x gives you a L-bit string. You calculate this thing that you have coded up, zeros of h of x, which gives you the position of the rightmost one in this h of x bit, in this h of x bit string. Well, and then you basically maintain a max of these. So this if thing that I've written says that if h of x, the zeros of h of x was gives me 10, and I had z to be like 8 before, then I set to be z to be the max of 8 and 10, which appears to be 10. So basically, z just maintains the max of these zeros of h of x over all values of x, and that's it. You're done. Voila. And your final estimate is this weird quantity, 2 to the power z plus half. What is happening? Any idea what is happening? But before that, let us quickly run through one particular example. So supposing, I mean, these colored balls that I saw, supposing I'm looking at only the user ID columns, and the colored balls are the user IDs. The colors are the user IDs. I don't know if you can distinguish the colors, but there's at least 1, 2, 3, 4 colors out here. So first you see the orange color. You calculate the h of x there, which is 0, 1, 1, 1, 1, 0, 1, and zeros of h of x is the position of the rightmost one, which is the position 0 out here. So zeros of so z gets the value 0. Then you get blue. I mean this deep blue. And then zeros of h of x again. Oh, sorry. So zeros of h of x becomes 0, 1, 1 when you see the orange. When you see the deep blue, zeros of h of x remains unchanged, right? Because the z remains unchanged, because z is the maximum of 0 and 1, which remains at 1. And then you again see orange, so z remains unchanged, and so on and so forth. So what is the value of z that you, maximum value of, what is the value of z that you see at the end? For this particular stream, if you go it from the left to right, 2, right? So you're stuck with z equal to 2 at the end. And then you return an estimate to the power 2 plus half. Where is this half coming from? I'll tell you at the end, but I'll just point you to where you can find the answer at the end. Okay? So first of all, let's see that what is the space usage of this algorithm, right? So so first we'll need to see how big L is, right? Because you're getting an L bit string. Well, if you do something like the birthday paradox, and that we can talk about later. I could convince you to say that, okay, having L to be bigger than, let's say, 3 log n is enough, right? That's enough. And very interestingly, the size of the Z has to be very small. And I'm claiming that it's small. It's enough to have it to be like log n bits. Why? It's enough to have a log n bit counter. Why is that? Because the maximum value of Z can take is only log n, right? So therefore Z itself, and if it needs to count only up to log n, then having log of log n bits is enough, right? So basically you have solved it in like space log n plus log n, which is, ridiculous, right? Even for, 1 billion log n is like, I don't know, 30. If I take the base 2 and then this is base 2, and then it doesn't matter anyway so much. So here is the intuition. I won't go into the proof. There's not that much time, right? See, what are we saying? We're really kind of keeping, so the basic intuition behind algorithm is as follows, that we say that every user ID gets mapped to a string, L-bit string, right? And we can consider that string to be uniformly distributed among the set of all possible L-bit strings, because we say that the hash function is a nice hash function like MD5 or something, and it maps something to a more or less uniformly distributed manner. So then if it's a uniformly distributed L-bit string, the chance that it's divisible by 2 is half. The chance that it's divisible by 4 is 1/4. Chance it's divisible by 2 to the k is 1 by 2 to the k, right? And so we expect it to be divisible by log base 2 of n. We don't expect it to be divisible by log base 2 of n plus 1, because there is not that many strings, right? And what Z is keeping is really this particular power of 2, the highest power of 2, right? That this is divisible by, right? And we could go do all this analysis. I won't show you all this analysis. I don't know if I even kept the slides, and I had deleted them, but and here is what we can get. What we say is that, okay, we can prove that with a reasonable probability. This is what we had promised. We get within, let's say, a 4 approximation, right? I mean that what we are, the answer that we are maintaining is at least 1/4 of the true answer, and at most 4 times the true answer. This is what we can get. Now, yes, your boss comes and say, yeah, what is this? 1 minus square root 2 by 2 is 1 minus 0.7. So only with 30% probability, you're giving me a good answer. But you said, so what? I'll just make multiple copies of this algorithm, right? And each of the copies will run independently. I'll return you a median of the answers. So these are standard tricks, okay? And then you can say that, okay, if I run 10 copies, the probability my algorithm will succeed is actually 1 minus 2 to the power minus 10. So which is pretty large. And all this analysis is not very hard, right? And in effect, it does not really increase the amount of space that you sort of use by that much. And surprisingly, it turns out that this is the problem. That this is really the underlying the underlying algorithm that's powering a bunch of companies' real-time analytics system, right, including the one at Yahoo, right? And if you look at this particular and they have kind of I had a small part initially to play here when we were kind of approached with this particular problem. So luckily enough, they also kind of outsourced the entire implementation, and they have a bunch of very smart people. When Lee Rhodes, Kevin Lang, and others, they added a lot of other streaming algorithms to it. And you can, if you're interested in actually implementation of what I just said, you can go to this GitHub. It's a professional sort of industrial level implementation available in a bunch of languages and has APIs in a bunch of languages. And what it allows you to do is that it's sort of in space kilobytes. I mean, of the order of kilobytes, you can actually answer these queries for where the original data sets are of size. I mean, imagine Yahoo sizes; they were of the order terabytes or petabytes, right? And now you can sort of process all of that in ridiculously small amounts of memory. You get some approximate results, but you're fine with it. You're not that much worried. And broadly speaking, this is the kind of goal that we have, that we're still pursuing, right? That we want to enable such kind of solutions for a lot of other statistical queries on very large data sets. And this becomes more interesting when the data sets have complex structure. For instance, what if it's a graph, right? What if it's a ranked list, right? And so on and so forth. And what if I'm not just estimating the statistics, I'm training ML models. Now, do these things have any kind of relevance there? It turns out it does. And once you hear, let's say, Ishita and maybe some other physicians talking about it, today itself in this open discussion, you will get to know more about it. And the motto that we tend to follow is that this notion of doing theory and doing practice goes hand in hand, because the kind of problems that we were sort of faced out here in sort of the kind of problems that we solved out here really came from practice problems. And in fact, in sort of implementing these data sketches, we had to improve a lot of the algorithms by Flajolet and others in order to make them have a little better practical performance. And that leads to a lot of nice theory, right? So theory and practice really do go hand in hand. Just to summarize, what I just talked to you today, if you look a little bit, this is called a streaming model of sort of processing data, in which what you say that the data set is huge, my machine is constrained in terms of the memory that I have, right? And the problem I talked to you about is estimating number of distinct elements. There's a very large set of such algorithmic problems that come from the combination of big data and trying to answer statistical queries to barely scratch the surface of it. So with this, I'll try to conclude because I have really overshot my, I think, huh? Okay. If somebody is interested, there's a bunch of other things. Okay, I really wanted to throw this puzzle for you to consider. And if anybody solves it, give an answer to me. That so forget this distinct counts. Suppose you are maintaining a dictionary or a hash map over a large universe. The keys are the items and the values are supposed to be the counts. How many times that particular item appeared in that data set? It's easy to do this if you are doing it in one pass and get counts of the items. However, what if I restrict all these values to be, instead of log f bits, where f is the maximum frequency, what if I restrict all the values to be log f bits, right? So I allow you only very small number of bits. And it turns out that this is also a practical problem that was faced by somebody called Robert Morris in designing the first Unix spell checker. Because at that time, the supercomputer that he had called PDP-11 had only 8-bit counters. And he was trying to fit a lot of counts into these 8-bit counters. And this has a very elegant solution. Again, a little approximate, but a very elegant solution. It can be done. So tell me if you can. And also, if you're interested in working in sort of the applications of some of these techniques to Nobel Prize winning sort of in fields, for instance, the gravitational wave search, that's also something that happens here. So feel free to talk to us if you're interested. And that's it, really. Now I'll shut up. Okay. Yeah. Thank you. Any questions?